Okay, so the next definition is beveled edge. And beveled edge has a lot of... beveled edge has a great number of things that we should probably talk about in terms of what beveled edge means. It obviously refers to how the edge of a door is treated, whether it be square-edged or it have a bevel to it. And the definition of bevel has changed in the hardware industry over the decades, and I'll point that out. How you measure backset is very much affected by whether or not you have a beveled edge, and to be mindful of that when you're reinforcing for something, or more commonly when you're drilling holes for something, function holes for a mortise lock, or a 2 1/8 inch hole for a cylindrical lock, things of that nature. And the glossary doesn't have a definition except it refers to edge, comma, beveled. So let's dive into all of that stuff right now. If you are enjoying this video, please click thumbs up or like, and also please consider subscribing to our channel. Let's move on to the rest of the video. Okay, let's dive into the definition, and what we have is our beveled edge definition. We are under beveled edge, C, edge, beveled. So we're going to go down to the E's for edge, and then there'll be basically a bullet point, I think, for beveled. Yeah, here it is, edge profile, beveled. The vertical door has a 1/8 in 2 slope from a plane perpendicular to the door pull side face. Okay, so what they're showing us here is 1/8 in 2, and that's really the definition. If you have a 2-inch thick door, which we never do, but if you had a 2-inch thick door and your door was 35 3/4, you know that from here to the other side of the door is going to have to be 35 1/2, because you've got 1/8 of an inch if it's a beveled edge door and it's 2-inch thick. Let's take a look at that, actually. So just using reasonable numbers, we'll say a 35, let's just say a 36-inch wide door, and then 35 3/4, 2-inch thick. So not wanting to rely on actually drawing it by hand, let's pull up a modern day version of a mechanical pencil and ruler. Okay, so this is AutoCAD, or AutoCAD Lite anyway. I'm going to draw a polyline, and I'm just for the sake of ease, I'm going to start it at the origin. So we're going to go 36 over. And then we're going to go 2-inch. And here's the trouble that we have. We don't know what angle to set it at. So let's just put it at a 90-degree angle, meaning it's not going to be beveled, which means that we need to be 36 here, and then we need to come down to 2-inch at 90 here, and then that's it. Now, we have a rectangle that's 36 by 2-inch. So what we can do from this point, though, is we can draw some more lines to give us some additional frames of reference. So let's draw a line here to here. Now let's draw a line from here to here. Okay. We know that it's going to be 1/8 of an inch over. So I'm going to draw a line from here, and I'm going to go over 1/8 of an inch. And the point of that is I can see where my line's going to end. My line's going to end right here, right below the 180. So actually, let's do that a little bit better. So line, we're going to go over 1/8 at 180, and then we're just going to come down. Actually, we won't come down. This dimension is 1/8 of an inch. We can see that. Let's go down to that corner, right to there. Okay. Now, let's clean this up. Trim. One-eighth and 2. That means that for every 2 inches, it's 1/8. That's the definition that they're giving us. So, let's now measure our angle. We know that it was 90 degrees until we inserted this 1/8 and 2 line. So let's measure angle between here and here. And it's telling me it's 86 degrees. Okay. If that's 86 degrees, then it's got to be 94 degrees over here, would be my guess. Measure angle from here. Measure angle here to here, 94 degrees. Very interesting. That's telling me that there's a 4-degree bevel on that line, based on 1/8 and 2. Well, that's a bit confusing because you may know that the industry standard degree is 3 degrees. Their definition is a 4-degree angle. Let's do this. Let's get rid. So remember that 4-degree angle. Let's draw something more typical, an 1 3/4 thick door. So 36, 0, 1.75. Now we know that it's 3 degrees because we're door people. So let's just say that this is a forgive me. We have a 1 3/4 thick line at 3 degrees. So what we're drawing here now is an 1 3/4 thick door with the same sort of square edge application. 36, 180, and then 1 3/4 and 90. Yeah, perfect. So now we've got the same rectangle, I think, except with this artifact here. Okay, now properties. 1 3/4 is the length of that. Now, let's do the same trick that we did before. However, this time, we aren't getting out to 2 inch because we're only getting to 1 3/4. So it's not, the offset of the line is not going to be 1/8 of an inch. So, we have to take that into account that our door is thinner than our previous example, so it won't be 1/8 of an inch. It'll be less than that. It'll actually be 1/8 of an inch. And in 2 inches there could be, let's just say that there are 8 equal parts. In 2 inch there would be 8 1/4-inch pieces. Because we're doing 1 3/4, that would be 7 1/4-inch pieces. So let's do 1/8 of an inch divided by 8 times 7. And when I do that math, there's a calculator here somewhere. Oh. Calculator. Divided by 8 times 7. Yeah, forgive me, that pulled up the calculator on a different screen. So what I'm saying is We're dealing with 1 3/4 thick. A common denominator between 1 3/4 thick and 2" could be 1/4 inch. So in 2" there are 8 equal 1/4 inch pieces. We're dealing with 1 3/4, so that would be 7 1/4 inch equal pieces. So 1/8 of an inch divided by 8 times 7, that gives us 0.109375. So 109375 basically means that from here over to where that slope is going to intersect here, it needs to be 0.109375. So let's draw a line, 0.109375 at 180 degree, enter, and then we're going to come down to this corner, just like we did previously. Okie doke. Now, as we did before, let's trim. Alright, now the question becomes is what is the angle? Measure angle between measure and angle, measuring it. Okay, measure angle from here to here, 86 degree. It's giving me the same 4-degree angle. That's what it's giving me. Now what's really interesting about that is our standard industry definition is 3 degree and not 4 degree. But when we're drawing it, it's clearly coming out at 4 degree. Measure angle. .4 degree, meaning it's a 94 degree angle in here. Now in my experience, 4 degree is a problem because your hardware is not meant to operate at 4 degree. It's meant to operate at 3 degree. Now let's continue the experiment a little bit. Let's draw let's just draw a line 5 inches in length. Say that line is 3 inch long, 0 degree. Let's draw another line now, 1 3/4. But this time, let's put it at a 3 degree bevel. Okay. Let's draw this line back to the perpendicular line. That's 1/8 of an inch. Which actually it's not that, it's 0.10975. So let's do this. .3" long, 0 degree. We're going to go up 1 3/4, and we're going to go at a 3 degree bevel. Now, here, we're going to go at 0.109375. 0.109375. Yeah, it's rounding, 0.109. Yeah, and that's probably where the error is. The machine is rounding. So when I put 109, it rounded it up to 1/8 of an inch. When I put 0.10 or 0.1, it rounded it to 3/32. So let's let that roll. 3/32. Wait a minute. Yeah, I got a little extra line here. 3/32. Yeah, okay. Now, we've got a 3/32 line. And what's happening here is I had the snap on, so it was taking the line in a direction that I did not want. So snap to get it started, 3-inch line, 0 degree. We're going to go up 1 3/4. We're going to go to 3 degree, which it is. Okay. Then I'm going to turn off the snap. I want this to be 0.1, which is going to give me 3/32. And then I'm going to draw a line, we'll just call it 2-inch, at 90 degrees straight down. Alright, so what we have here is a 3 degree or an 87 degree angle. Let's test that angle between here and here. 87 degree. Okay, great. Now, we know that we've got an 87 degree angle, or a 3 degree bevel is really what that is. Let's measure what this distance is. Well, we know what the distance is because we set it. Yeah, distance. From here over to here. Yeah, it's 3/32 of an inch. So the entire problem was that 1/8 and 2 was giving us a 4 degree angle. But when we know that the angle is 3 degree, which is what we know it to be, we get a little different result. So the point of all of this is 1/8 and 2, according to AutoCAD, is giving us 4 degrees. Our industry definition is 3 degree. But what's really interesting also is that the definition has changed over time. And what I mean by that is I happen to have some really old Yale catalogs. So on my website, when you get to the manufacturer's page, and we open up, let's open up the 1889 catalog. And while that's loading, I'm also going to load the 1910 catalog. Alright, so that's the 1889 catalog. And I search for the word bevel, and you can see that in 1889, all front door and vestibule locks and latches are regularly made by us with a bevel of 1/4 inch and 2 1/4 inch. A 1/4 inch bevel and 2 1/4, but this bevel can be altered to suit, and the method of measuring the bevel is shown on page 15, which I think that's a typo, because it's page, I believe it's page 17. So here's what they're showing in 1889. A 2 1/4 inch thick door has a 1/4 inch relief there. So we could put that in AutoCAD and determine that angle. I suppose let's just do that. Three, 0, 2 1/4 at a 90 degree angle. Okay. Now we're going to go over a 1/4 inch here, 0.25 at 180 degree, and then we're going to come right back down to the origin. Bingo. So now we've got a 2 1/4 inch thick door, and let's measure that angle between this line and this line. Now that's a 6 degree. That's a 6 degree angle. Okay. 6 degree. It's double what our modern definition is. So let's do this. So in 1889, it was 2 1/4. It was 1/4 in 2 1/4. Now in our 1910 catalog, which I've got loaded here, let's look at the definition of bevel here. Now here they're showing it the standard bevel is 1/8 in 2 1/4, so they literally cut it in half in terms of the angle. So let's just do that now. So let's go, it's 1/8 in 2 1/4. So let's go line 3 inch 0, and then let's go 1/8 and 2 1/4. 2 1/4 at 90. Okay, got it. Now let's go. Let's go 0.125 at 180. Good. Now let's come back down to the origin. Not the origin, but you follow my meaning, I hope. Okay. (1889) definition, 1910 definition. Let's measure the 1910 definition. Measure angle between this line and this line. (3 degree). That's a 3 degree angle, is what that is. But then they changed the definition to 1/8 and 2. And rather than 1/8 and 2 1/4. But at this point, we're getting down here. Okay, let's do this. Let's draw a line from the base. Let's go up 2 inch. Let's draw another line. I should have just kept that line going. Line. Let's just go over we need to go 1/8, 0.125. And then we're going to come back down to its origin. Now we're going to measure that angle. Turn off the snap. We're going from here to here. That's a 4 degree angle. So they've gone from a 6 degree angle in 1889 to a 3 degree angle in 1910 to a 4 degree angle in modern times. But we know that the bevel that we all use is 3 degree. Or at least we may know. So it has sure changed with time. Now, to really bake your noodle about this, in 1910 they explain, they make some statements here. That is yet a different way to think about it. The proper bevel of a door, if any is needed, is determined by the size of the butt, which means the width, because how far the hinge, the vertical axis of pivoting is from the face of the door really matters. And let me show you what really matters means. WTBD 1168. I have a video of a video of a 5x12 hinge. Well, yeah, it's here. But basically, what we have here is we've got a pivot point that would be reflective of a 12-inch wide hinge. And when you get over here, a standard 1/8 of an inch margin between the door and frame simply does not work. It just doesn't work because there's not enough room. The gap between the edge of the door and the jamb is too small, or the bevel is not aggressive enough. So how far off this pivot point is, or the width of the hinge, is what they're talking about. So it's based on, it's determined by the size of the butt, and they mean the width. The height doesn't matter. And a width of the door. So how wide is the door? But what's really interesting about that is, is this. Okay. Let us draw a polyline. Say it's 36. Let's say it's 1 3/4, and let's say that it is just at 90 degree. Let's go back 36 at 180 degree. And let's go 1 3/4 at 0 degree. I'm sorry, at 90? Nope, at, yeah, 270. All right, now, and the artifact. All right, let's get rid of the calculator. So what's really important, if this door swings out in this direction, what's really important is this corner right here. And what their next definition is referring to is that corner. So what I want to do is put my pivot point, and from here to here, it's a 1/4 inch. Okay, great. So come out 0.75 at 90. 0.75 at 90. Okay. I want to, and just bear with me as I do this. That's going to be my vertical axis of pivoting right there. Except it's not going to be there. It's going to be, if I've got an 1/8 of an inch margin between the door and the frame, this line is an 1/8 of an inch. Okay, so that's good. So what we want to do is we want to take this, group it, let's move it right there. That's going to be our vertical axis of rotation for the door. So the door is a polyline, so it's basically grouped. Let's rotate it. You're going to pick a base point, which is the vertical axis of pivoting, which we've got a little screwed up here, but it's so close it doesn't matter. So what they're saying in the next part of the definition, which I'll show you, is that outside corner is going to follow along an arc. And you can see when it's in, the door is in the closed position, if you have a square edge door, you can see how it encroaches into the space. Right there. And that's why you need a bevel on the door, or you need more gap I'm playing with an 1/8 of an inch gap. You would need gap between the door because of the fact that the door is going to rotate around that corner. So what happens is there is a circle that's being created here from that inside corner. That corner is going to observe the path around a circle. And that illustrates why we have to have a bevel on the door, because it makes for a tighter fit, is the point. If you don't bevel the door, you have to have more margin between the edge of the door and the jamb. But if you bevel the door, you can have a tighter margin. And the question becomes is, what is the bevel of the door and what kind of margin do you want? And the current definition is 3 degree. And when you have a 3/0 door, a 3/0 wide nominal opening, and you've got a wood door, when you put a 3 degree on both styles, you're going to have a door that's 3/32 smaller between the lock side of the door and the strike jamb, and the hinge style of the door and the hinge jamb. And that's just what that is. But now we can see why. But what's equally interesting is how the definition is changed. But what Yale does, they tell us the inner corner B, which I was just demonstrating, travels on the radius of AB. It does. I was turning my circle around, as shown in figure 12. The inner corner B of the door travels on the radius AB and must have a clearance equal to the versed sine of the arc BC. Now, without going into the math of this, so what we could do is we would create a couple of angles, a couple of triangles in this space. We would use trigonometry, and then we would, along that angled line, which maybe it's going to be the hypotenuse in a certain respect, a line at 90 degree back to that corner, we're going to get an angle of about 1.5 degree is what it is. So this line right here is just a ton of math. And you could deep dive into that by searching math formulas, or maybe you just remember trigonometry that well. Inner corner B travels along the radius of AB. We understand that. The circle goes around. And must have a clearance equal to the versed sine of the arc. So what this basically is I think -1 to the square root of cosine or something like that. I'd have to look it up. Of the arc BC. This may be obtained by beveling the edge of the door, or if its edge is left square, by leaving a sufficient clearance between the door and its jamb. If the door is of fair width and the butt does not need to be very wide, the width of the hinge, to clear the architrave, meaning, the woodwork that's here, it will be found that a square-edged door may be used without resort to an unduly open joint, meaning the margin here to be excessively wide, thus permitting the use of a lock with a regular front, meaning a front of a mortise lock that's not going to need to have a beveled sort of inherent design to it. The use of beveled front locks should be avoided when no real need for them exists. So there's mathematics involved to determine this, which is not going to end up in a result that matches 1889, that matches 1910, or that matches 1/8 and 2, or the current definition. Okay? And they're saying, if your gap is wide enough here, and your hinge, and why did I select 3/4 inch? Well, that's typical for a hinge or a pivot. And I do stock 12-inch wide hinges, which is why I drew this, so that people can see, wow, you really need to think about what you're doing there. And then we get back to, why do we use 3 degree today? Because it's really not required. You can get by with less. We can prove that by using AutoCAD. But at the end of the day, I think 3 degree is a reasonable compromise between what the math here would say it needs to be theoretically and an extremely heavy definition as it was previously. Okay, if we recall. And a 3 degree bevel simply allows for a small amount of increase in the size of the door, maybe as a result of thermal bowing on a steel door, or maybe a wood door in a very high moisture environment. So I think, and I don't know this, but 3 degree just must simply be a compromise. And it's probably been found to simply work. And that's the bottom line. It just is found to simply work. So if you were to investigate the mathematics on this, and I tap the shoulder of someone with a master's degree, two people with a master's degree in mathematics, if you were to try to learn the mathematics of what's being explained here, it's not going to give you 3 degree. It'll give you a value that will work theoretically, but if you go to install doors using this formula or this approach, your doors may not work right. Because after, I don't know, 200 years of hanging doors in the United States, well, more than that obviously, a few hundred years, 3 degree has just been arrived at based on it's a tried and true dimension. Now, talking about beveled edge, let's return to the glossary here. And they're showing you beveled edge. But the next part of the discussion is what edge is beveled? Let's talk about that on camera. If you've not hit subscribe yet, we would very much appreciate if you did, and hopefully you're enjoying this video. Now, let's get back to it. So the next part of the question becomes, what's beveled? You know, you've got two styles. So a door can be square-edged. Very typical, very common. Residential doors will be square-edged very, very often. Not unusual at all. You can have one style beveled, or you can have two style beveled. So you can have square-edged, you can have beveled one edge, or beveled two edges. So what we would end up saying is the shorthand that we use is 3 degree 0, meaning 3 degree at no styles, at 0 styles, or 3 degree 1 lock. That tells me on the lock style, put a 3 degree bevel. Or 3 degree 2, that means both styles will be beveled. Now, residential doors will be very commonly square edge. They'll have margins that are 1/8 of an inch. You're not going to have a problem with that door rotating. Some old-timers, they want the lock style beveled, but would never bevel the hinge style, and they would say that's because it's not necessary. But they will concede, they'll acknowledge that, well, sometimes you get hinge bind. So what happens is when you don't bevel, when you're going to bevel the lock style, we can now understand why that's advantageous. It pulls that point B further away from the frame so that it can actually move rather than being up tight close to it. A square hinge style is, to me, not ideal, and I would always bevel the hinge style, even though old-timers, going back to my early career, there was one gentleman that I always think about. His name was Pete Loeb Carpentry, and he was the absolute definition of old-timer in the sense that he would come in with his carpenter pencil and his, you know, behind his ear, and just looked like a carpenter. He looked like the, you know, if you asked ChatGPT for images of an old-time carpenter, his picture would come up. He looked like he had sawdust on him constantly. And he would tell you, no, you don't have to bevel the hinge style. It's true in lots of instances, except that when you close the door and it springs open a little bit. And what my argument is let's relieve the hinge style a little bit, because if that jamb is here, well, the jam's supposed to be true plumb level and square. And that same old-time carpenter, Pete Loeb, with his carpenter's pencil, which is a very thick pencil, they're not getting into the minutia. They're not getting it into the 3/32nd, the very 0.109375 dimensions, because they would never acknowledge that as being important. But at the end of the day, if that jam's not true plumb level and square, and it's got a little bit of twist on it that is imperceptible, all but imperceptible. And you close that door and it just springs open a little bit. Yeah, it's because you got a square edge door. Now the problem is also in the design of the hardware. Meaning, and I happen coincidentally, it is actually a coincidence because I'm making a different video on this. I've got two hinges here. And let me tell you, they look identical. And let's talk about what they look like. If you are enjoying this video, please click thumbs up or like, and also please consider subscribing to our channel. Let's move on to the rest of the video. So, two hinges. They're both McKinney hinges. One is a TA2714, a Super Garden Variety hinge. I don't know which. It's one of the two of these. The other is a TA4314, not a Garden Variety hinge. You don't see them often. But I can tell, we're going to figure out which is which right now. When I bring the two leaves parallel, if you've ever looked at a hinge template, that's an 1/8 of an inch gap between there on a standard weight hinge. Okay, just kind of memorize what that looks like. Those leaves are parallel and the gap is consistent. This is clearly the TA4314. When I bring the leaves parallel, I really can't bring the leaves parallel. And that's because the bend on the leaf on this hinge is different than the bend on the TA2714. And that's because one hinge is truly meant for a square edge door, which is this one, and one hinge is meant for a beveled edge door. Now, the problem is TA4314 and 4314. We'll look in the McKinney catalog. No one ever orders these hinges. No, I don't stock them. I don't know that anyone does. And in decades, it's never really been an issue in terms of full mortise hinges that are just garden variety hinges. Now, you'll bump into needing to define to your hinge manufacturer when you have an anchor hinge or a swing clear hinge if you have square or beveled edge doors, because they're going to put a different bend on the hinge here. They're literally going to bend it different. Not bend it different. It'll be the same bend, but the angle is what's going to be different. Okay, and now you can see what that means. If you're installing regular hinges on beveled edge doors, it's going to work, but your experience of bumping into hinge bind is exasperated by the fact that it's really the wrong piece of hardware, and that you should have a hinge that has a 3-degree bevel on it, or a compensated 3-degree bend on it. And that's indeed what that is. Okay? So bevel is important to define where the bevel is, because it very likely will affect everything. You're beveling a door so that it fits better. You're beveling a door so that your margins can be marginally tighter. And it's really only the difference between an 1/8 of an inch and 3/32 of an inch, which is 1/32 of an inch, which is 0.03 basically. If you took an 1/8 of an inch and you cut that in half and then cut that in half again, that's what we're talking about. It's tiny. But if you ever bump into a door that's hinge bound, it's a confluence of all of these things not being exactly the best way they could. And I like to tell people, well, a 16th here is no big deal, but if you have a 16th and a 16th, now you got an 1/8 of an inch. Now it's a problem. So the cumulative effect of a jamb that's not true plumb level and square, of a door that's square edge or beveled edge when you've got a regular hinge on it, and you have taken an application where you've not beveled that edge, or or the door is too wide to begin with, or whatever the case might be. All these little things have a cumulative effect to give you the less than ideal operation of the door that you can then visualize. You can see it, and it's that cumulative effect. So 3° 0 square edge, 3° 1, it's going to be the lock side. No one's really ever ordered a square edge lock style with a beveled edge hinge style, unless it's an inactive door. Then that's what you want, actually, because you want that strike, the flush bolts, to be on a square edge, because then you'll bevel both styles of the active door, and that's the last way, 3° 2. You're beveling both styles. Now, I can tell you from real experience that if you make doors that have a greater than 3-degree bevel, not only is it going to look weird, but your hardware is not going to fit right. So the latch bolt on a cylindrical lock or the armor front on a mortise lock, that's all meant, a lot of the times, it's meant to adjust from square to beveled edge doors. But if your door edge is too great, your bevel is too great, standard manufactured hardware is not going to fit right. Those hinges won't fit right because it's meant for a 3-degree bevel. We made 25 years ago 150 plastic laminate doors, and the saw, it wasn't a saw, it was a CNC tool. It was cutting the bevel at 4 degree, and we shipped all these doors to the site, and the reports came back. The doors aren't fitting. The hardware's not being flush with the edge of the door. And we got a door back, and we realized you could see it actually, and I was amazed that it even left the shop. You can tell that it was too aggressive of an angle. So again, how 3 degrees been arrived at, it's a bit of a mystery in the sense of who decided it's 3 degree, gavel down. But 3 degree works. The hardware manufacturers make for it to work. The door manufacturers make for it to work based on prefits. The old timers understand what to do with it, and everyone else in between. So it's important to think about the beveling of the door, or the edge of the door. And beveled edge doors are important to really understand how they change your understanding of backset. And this isn't a definition explanation on backset, but we do need to talk about it. So let's switch to the screen view.
If you've not hit subscribe yet, we would very much appreciate if you did, and hopefully you're enjoying this video. Now, let's get back to it.
Okay, now in a prior definition, I have defined backset, and I've used this same sort of analogy, and if you recall our SDI definition, it literally shows these 4 door types. And I'm not going to say that they got the idea from me, but here they are. Just what I drew. Beveled edge, radiused edge, rabbited edge, square. Okay, so backset, and what's really great about backset is it's the definition from the edge of the door to the center of the hole. Edge of the door to the center of the hole. That's your backset. Backset. So edge of the door to the center of the hole. So backset. Edge of the door to the center of the hole. Edge of the door to the center of the hole. You get the concept. Edge of the door to the center of the hole. Great. Well, if you put your tape measure here and went back 2 3/4 and drilled, and you did that same trick here and went back 2 3/4 and drilled, it's going to be a different dimension. And that's because you've got 1/8 of an inch in 2, so that's going to be almost a 1/16 of an inch difference between hooking my tape measure here going back 2 3/4 and hooking my tape measure here and going back 2 3/4. 2 3/4 is a typical backset for a commercial lock. Now, if you're a 1/16 of an inch off on a lock set, probably not a big deal. But if you're a 1/16 of an inch off on a door viewer, it probably is a big deal, and here's why. You're drilling your door viewer, let's say it's going to be at 18 inch. 18 inch over, you mark on the other side of the door 18 inch over, and you drill. Great. Well, now try that trick on this door. 18 inch over, 18 inch over, and now you're off 1/8 of an inch. And the margin on the trim of a typical door viewer is quite small. And this is a large door viewer. You could have, I think it might be a 624 by Rockwood. Yeah, this is a tiny door viewer. Much smaller trim piece on the inside. So if you try that trick, you're going to have a problem with your door viewer. The lock, you're going to be almost 1/8 of an inch off. And you'll see it when you drill through the door. Now, the important part is bevel has everything to do with understanding backset, because backset is actually defined from the center of the thickness of the door. So when you're measuring your backset, you have to know Am I dealing with a square edge door or a beveled edge door? Same logic with these guys. If you're doing atoms right in a radius aluminum storefront, it's measured right from here. So beveled edge is really important when you're understanding backsets. Also, backsets have everything to do with reinforcements. I mean, where are you going to put the reinforcement for a Dutch door bolt on the top leaf of a Dutch hollow metal door? Well, you want to know where that's being referenced from. So whether it's beveled edge or rabbited edge, which it could be on a Dutch door, it's important to know that. So let's take a look at the... That's the definition. And our next definition after bevel is blank jam. Okay, so what we're going to do in the next part of the video, which I'm going to go over an email that I received back from one of my two mathematicians I mentioned. They both come out of secondary education with master's degrees. I have a written response from one of them, so let's look at that now.
If you are enjoying this video, please click thumbs up or like, and also please consider subscribing to our channel. Let's move on to the rest of the video.
Okay, so take a look at the figure is what, and I'm just going to credit him, Ralph Forrest Ball. He is an ALOA ACE instructor. He works for ALOA. He is a former high school math teacher, if I recall. It was high school math. He has a master's in mathematics. He owned his own very successful lock shop for a long time, and he teaches classes at ALOA. And because I've been a student of his and I knew his mathematical background, I reached out to him. So he says, take a look at figure 18, and he's showing us figure 18, which is out of the 1910 catalog. And what Ralph is saying, imagine that the door frame doesn't exist. Imagine that the hinge pins are a single continuous pole that is cemented into the ground. You can tell that he was a high school math teacher. I call it the vertical axis of pivoting, but the way his bedside manner makes it very approachable. The door could swing 360 degrees around this pivot point, as we illustrated by our little trick of this. Okay. Any point along the door would trace out a circle as the door swings around. Yes, we discussed that. Now let's bring the door frame into the picture. Point C is the corner of the door frame. We are worried that the door itself is going to rub against the frame, possibly get stuck there. Indeed, that's the whole purpose of the concern. C, is the door going to hit here? Let's say we know the distance from the hinge pin to point C is exactly 36 inch, and it can be, because from here over is 36 inch. It could be anything. It doesn't matter what it is. In reality, it would probably be, it's going to be a very small fraction smaller than that, but it just doesn't matter. Anything less than 36 inch from the hinge pin could swing 360 degrees without hitting the point C. Anything more than 36 inch is going to hit point C. So what he's saying is, and I really appreciate his approach again, because he makes it very digestible. If this is 36 inch, it'll rotate around. If it's bigger than that, it's going to hit. Pardon me. If it's smaller than 36 inch, it'll rotate around, as we're doing here. If it's bigger, it's going to hit. Okay, we understand that part. Now look at point B. That's the point on the ingress side of the door, which is exactly the same distance from the hinge pin as point C. So he's saying, Ralph is saying, point B is the same distance as point C from the hinge pin. Interesting. So I think what he's saying is the ray AC and AB are the same length. Okay, let's go with that. Any portion of the door which is further away than point B would hit point C when the door tries to swing. The only way that the door can swing is if there is no wood at all in the door to the right of point B. To the right of point B is this area here. Wood's got to go. He's really elegantly building the case for this is why the door has to be beveled. He's saying if it's not beveled, I think, you're going to have a problem. How can we accomplish this goal? Point B must become the edge of the door on the ingress side. And by the way, the ingress side, what Ralph is saying is this side of the door, the push side, is the exterior. This is a residential application. The door swings into the home. This is the ingress side, whereas the pull side would be the egress side. Point B must become the edge of the door on the ingress side. One option is to bevel the edge of the door back to point B. Then we'd need to figure out how much of a bevel is required. We'll come back to this in a minute. Unfortunately, this also means we'd need a latch that has a beveled face. Well, that's typical for hardware. Or can pivot slightly to match the bevel of the door. They do. The other option is to make the door less than 36. Okay, suppose point B is 35 3/4 from the opposite edge of the ingress side of the door. If we just make the door 35 3/4 instead of 36, then point B can swing as and miss just barely point C. So his argument is make the door smaller than 36. In fact, make it 35 3/4, and it won't hit the jamb. The downside of this is that we've created a 1/4 inch gap between the edge of the door and the frame. Are you okay with that? If so, we're done, problem solved. Well, we're not, because a 1/4 inch gap here is too heavy. It just is. 1/8 of an inch is on 1/8 of an inch actually is the outside of what's acceptable. Let's give some support or context to that. I'm going to pull up my copy of NFPA 80. Standards for fire doors and other opening protectives. Okay, bear with me. We're going to get to clearance. I think we want 6317. Here it is, 6317.1, clearances. This is, NFPA 80 is the standard governing fire doors. Clearances between the top and vertical edges of the door and frame and the meeting edges of doors swinging in pairs shall be 1/8 of an inch plus or minus a 1/16 for steel doors and shall not exceed 1/8 of an inch for wood doors. So when Ralph asks the question, are you okay with that? The answer is no, we're not okay with that. Because in the commercial world, we're probably dealing with fire doors a lot of the time. Moving on, what if point B is 35 1/2 inch from the opposite side of the ingress side of the door and we decide that a 1/2 inch gap is unacceptable? Then we're back to the beveling option. Here's how we do it. We draw a triangle with one corner at point A and the other corner at point C, and the third corner at approximately point B. The exact location of B isn't important, we just need our best guess. What's important is that we need to know the size of the acute angle at point A. Just eyeballing it, it looks to be about 2 degrees. So, what Ralph is saying is, he's basically got, it's drawn here. We've got a triangle. Where this exactly is doesn't matter. He's basically saying this angle looks like it's about 2 degrees, and what he's going to get us to is helping understand what the other two angles are, I imagine. To calculate it, we need to use a bit of trigonometry. If ABC is a right angle, then the sine of angle A is equal to the opposite side divided by the hypotenuse. It's okay if we're slightly off. We just need an answer which is close enough. The hypotenuse is 36 inch. We just need the length of the opposite side, which is the distance from C to B. Okay, that's basically the door thickness. The difficulty is that we don't have an exact location for B, but that's okay. Suppose we know the thickness of the door at 2 inch exactly. We can see the distance from C to B is more than 2 inch because it's closer to 3 inch. And what Ralph is saying there, he's basically saying if this is a 2 inch thick door, well, this is greater than 2 inch. And I'm going to say it's about 2 3/4 if we're going to go with Ralph's. That hinge is probably 3/4 or 1 inch. Could be that. Therefore, the sine of angle A is 3/32 or 0.083 inch. We could use our calculator to find out the angle in degree by typing 0.083 and hitting inverse sine, it's 4.78 degree. But we don't actually need to do that because what we really want to know is how far back does the door need to be beveled. The answer is the sine of angle A times the thickness of the door minus the current gap between the door and frame. And the problem with a lot of this is we're assuming what the gap is. We don't know what it is. We're making an assumption. And what I'm trying to say is in the 1910 catalog, they're giving us in one sentence 2,000 years of evolution of mathematics without us knowing all of the details. Ralph goes on to say, let's say the gap is 1/8 of an inch. Remember the door is 2 inch thick. The sine of angle A is 0.083. We multiply times 2 inches to get 0.166 inch minus 1/8 of an inch gives us 0.041. That's the minimum we need to shave off the ingress side of the door. In reality, we probably want to keep that 1/8 of an inch clearance, so don't subtract 0.125. Just keep the measurement of 0.166 and shave that much off the edge of the door. Or we could just bevel the door by 4.78 degree if we have a protractor. To get a precise answer is a lot harder, but it would still be a question of right angles and trigonometry. Now, you could do a deeper dive on this. There's a gentleman online who has made an extremely deep dive into it's here, door bevel calculation on YouTube. This is
Hi everyone.
You know, if I were to study and read this enough, I will be able to digest what this all is. But this is a really great little cheat right here that he's showing. It has everything to do with dealing with a right angle, because once you have a right angle triangle, you can determine the other angles using not basic trigonometry, but trigonometry. And he goes on through the video to really get us some hard answers. And at the end of the day, all the way at the end of the video, it's not 3 degree. In fact, it's about half of that. And when I ran the math using the formula to the inverse sine, as Yale says it, I got 1.505 degree is what I got, which is about half of what the current standard is. I mean, what the industry definition is. So at the end of the day, it's 3 degree. Why is it 3 degree? That's because that's what we want it, is the answer. Beveled edge, it's 3 degree. Why? That's what we want it to be, is the answer. The other mathematician I spoke to is a high school math teacher in Lee County, Florida. I'll leave her identity less than transparent because, you know, she's not necessarily publishing articles like Ralph Forrest Ball is in Aloha in the Keynotes magazine. Ralph has a really interesting approach to locksmithing because of his heavy mathematics background, and it's very enjoyable to be in his class. Advanced Master Keying Specialist is, I believe, what it was. Let's wrap up this video on camera. Now, in conclusion, that talks about a beveled edge door. At the end of the day, all you need to know, it's square edge or it's beveled. If it's beveled, it's going to be a 3 degree bevel. If you're following standard industry conventions, because that's what your hardware will be made for. But if you are doing beveled edges on the hinge styles, think about those beveled edge hinges from McKinney or anyone else who makes them. I just think of McKinney when I think of those because it's right there in their catalog. It's pretty obvious. Let's move on to the next definition. Thank you.
Thank you for watching, and if you've enjoyed this video, please click thumbs up, please subscribe, and maybe even send the video to someone that you know. Thank you.